What is supernova? How many types of supernova? What is the role in galactic evolution? A supernova is a powerful and cataclysmic explosion that occurs at the end of a star's life cycle. It is one of the most energetic events in the universe and can briefly outshine entire galaxies. Supernova play a crucial role in the creation of heavy elements and the dispersal of these elements into space, which is essential for the formation of planets, stars, and even life as we know it. Types of the supernova. Type I supernova, thermonuclear supernova. Type I supernova, often referred to as thermonuclear supernova, are a remarkable class of stellar explosions that result from the runaway nuclear fusion of matter in the core of a white dwarf star. These explosions are characterized by their extreme brightness and nearly uniform luminosity, making them crucial tools in the field of astrophysics and cosmology. The progenitor systems of Type Ia supernova typically involve a white dwarf star in a binary system, where the white dwarf slowly accumulates matter from its companion star. As the white dwarf's mass approaches a critical limit known as the Chandrasekhar limit, approximately 1.4 times the mass of our Sun, the core temperature and pressure reach conditions where carbon fusion can rapidly ignite. This ignition triggers a violent and explosive chain reaction, causing the white dwarf to completely disintegrate in a matter of seconds. The release of energy in a Type Ia supernova is staggering, briefly outshining an entire galaxy and producing a distinctive light curve that can be observed from Earth. Because these supernovae have such consistent luminosities, they serve as valuable standard candles in astronomy. By measuring the apparent brightness of Type Ia supernova and comparing it to their known intrinsic brightness, astronomers can accurately determine their distances from Earth. This has been instrumental in mapping the expansion of the universe and discovering the existence of dark energy, a mysterious force responsible for the accelerated cosmic expansion. In addition to their cosmological significance, Type I supernova also play a critical role in the synthesis of heavy elements, as they eject material rich in these elements into space. This enriched material can eventually contribute to the formation of new stars, planets, and even life. Overall, Type I supernova are celestial laboratories that provide valuable insights into the workings of the universe, from the life cycles of stars to the fundamental properties of space and time. Type II supernova, core collapse supernova. Type II supernova, also known as core collapse supernova, are a class of powerful and cataclysmic stellar explosions that result from the collapse of the core of a massive star. These supernovae are characterized by the presence of hydrogen lines in their spectra, indicating the presence of hydrogen-rich material in their outer layers. Type II supernova are among the most energetic events in the universe, marking the dramatic end of the life cycle of massive stars, typically those with masses at least 8 times that of our Sun. The process leading to a Type I supernova begins when a massive star exhausts its nuclear fuel. As a result, it can no longer produce the internal pressure needed to counteract the gravitational forces trying to collapse its core. The core rapidly contracts and heats up, eventually reaching temperatures and pressures sufficient to initiate a series of nuclear fusion reactions. These reactions, involving elements like helium and heavier elements, release an enormous amount of energy, causing the star's core to expand and rebound violently. The outer layers of the star are ejected into space in a brilliant explosion, while the core may collapse further to form a dense remnant, such as a neutron star or, in some cases, a black hole. Type II supernova play a crucial role in the universe, as they not only distribute heavy elements forged in the explosion, but also trigger the formation of new stars and influence the evolution of galaxies. Their study has provided valuable insights into the dynamics of massive stars, nucleosynthesis, and the life cycle of galaxies. Nucleosynthesis. Nucleosynthesis is the process by which atomic nuclei are formed through nuclear reactions in various cosmic environments, such as stars, supernova, and the early universe. It plays a fundamental role in the creation of chemical elements and the enrichment of the universe with a wide range of atomic species. Primordial nucleosynthesis, Big Bang nucleosynthesis. Primordial nucleosynthesis occurred during the first few minutes after the Big Bang, when the universe was extremely hot and dense. At that time, the conditions were suitable for the formation of light elements, primarily hydrogen, H, helium, He, and traces of lithium, Li, and beryllium, B. The primary reactions during primordial nucleosynthesis included nuclear fusion processes, where protons and neutrons combine to form helium nuclei, He4, and some small amounts of deuterium, H2, helium-3, He3, and lithium-7, Li7. Stellar nucleosynthesis. Stellar nucleosynthesis occurs within the cores of stars during their various stages of evolution. Stars are massive nuclear reactors where the intense heat and pressure allow for nuclear fusion reactions to take place. The primary process of stellar nucleosynthesis is the fusion of lighter elements into heavier ones through a series of nuclear reactions. This process releases energy and is responsible for the creation of most of the elements in the periodic table. The main stages of stellar nucleosynthesis. Hydrogen fusion. In stars like our Sun, hydrogen nuclei, protons, fuse to form helium through a process known as hydrogen fusion or stellar hydrogen burning. Helium fusion. In more massive stars, helium nuclei fuse together to create carbon, oxygen, and other heavier elements. Helium fusion occurs via the triple alpha process. Carbon and oxygen fusion. In even more massive stars, carbon and oxygen nuclei undergo further fusion to produce elements like silicon, sulfur, and iron. Supernova nucleosynthesis. During a supernova explosion, extreme conditions allow for the rapid formation of even heavier elements, including elements beyond iron on the periodic table. Supernovae are responsible for the creation of elements like gold, silver, and uranium. Nucleosynthesis is a crucial process for understanding the chemical composition of the universe. It explains the origin of elements and the distribution of elements in galaxies, stars, planets, and, ultimately, life itself. The study of nucleosynthesis helps us trace the history of cosmic evolution and provides insights into the life cycles of stars and the formation of the elements that make up our world. What is the role in galactic evolution? Nucleosynthesis, the process by which atomic nuclei are formed through nuclear reactions, plays a significant role in the evolution of galaxies, including our own Milky Way. Here's how nucleosynthesis contributes to the evolution of galaxies, including its impact on the chemical composition and dynamics of galaxies. Chemical enrichment of galaxies. Nucleosynthesis, occurring primarily within stars, enriches galaxies with a wide range of chemical elements. Stars synthesize elements from hydrogen and helium, which were the predominant elements produced during the Big Bang. Over billions of years, these elements have been transformed into heavier ones through nucleosynthesis processes. Stellar populations. Galaxies are composed of various stellar populations with different ages and chemical compositions. Younger stars, formed more recently, tend to have higher abundances of heavy elements because they inherit the enriched gas from previous generations of stars. Older stars, on the other hand, formed when the galaxy had lower metallicity, fewer heavy elements. Star formation rates. The availability of heavy elements influences the rate at which stars can form in a galaxy. Regions with higher metallicity, higher abundance of heavy elements, are more conducive to star formation because heavy elements act as coolants, allowing gas clouds to collapse and form new stars. Stellar evolution. The evolution of individual stars is affected by their initial chemical composition. Heavier elements impact a star's internal structure, energy generation, and lifetime. This, in turn, influences the types of stars that exist in a galaxy and the duration of their various evolutionary stages. Galaxy dynamics. The distribution of elements throughout a galaxy affects its dynamics. Elements, especially heavy ones, contribute to the overall mass of a galaxy and influence its gravitational interactions with other galaxies and cosmic structures. Chemical evolution models. Astrophysicists use chemical evolution models to simulate the buildup of elements within galaxies over time. These models take into account factors like star formation rates, stellar lifetimes, and nucleosynthesis processes to predict the chemical composition of galaxies at different cosmic epochs. Metallicity gradients. Many galaxies exhibit metallicity gradients, where the abundance of heavy elements varies with distance from the galactic center. This gradient reflects the history of star formation and nucleosynthesis processes within the galaxy. Cosmic recycling. Elements synthesized within stars are eventually released back into the interstellar medium through processes like stellar winds, supernova explosions, and planetary nebulae. These elements are then incorporated into new generations of stars, planets, and, in some cases, life forms. Stellar archaeology. Observations of the chemical compositions of stars in different regions of a galaxy provide valuable information about its past and the nucleosynthesis processes that have occurred throughout its history. Nucleosynthesis is a fundamental aspect of galactic evolution. It shapes the chemical composition of galaxies, influences their dynamics and star formation, and provides insights into the history of cosmic enrichment with heavy elements. The study of nucleosynthesis within galaxies is essential for understanding their formation, development, and the diversity of stellar populations within them. That's all in this video. If you like the information, please hit like and subscribe to this channel, and be connected to this channel for more space information.